take much longer. I have two possibilities. We're going to do both of these things, but the question is which one to do first. I can talk about the homework, and particularly the nonlinear term aspect. I can do that. Or I can talk about random vibrations of a linear system. We're going to do both. So you can't, on the one hand, if you like both topics, you won't be disappointed. On the other hand, if you hate one topic or the other, you're going to hear about it anyway. So it's a question of which topic would you like to hear about first? This is democracy. We take votes. Of course, I have a veto. An absolute veto. Which one would you like to hear about first? The nonlinear homework or the...
Yeah, homework.
Homework. Oh, okay. Now, the only reason I'm reluctant is some of you have been working hard on the homework, and all of you have been working hard, I'm sure. But some have probably made more progress than others. Some may have devoted more time than others. So I'm going to reveal some things. If you've been working hard, you may be shortchanged because your colleagues who may not have worked quite as hard on it will hear the benefit. But you're okay with that, right? Because we're a team. And it doesn't matter what your grade is. We're just here to learn, right? No one's interested in what their grade is. Is that true? Yeah. More or less. Okay. All right. So let's talk about the homework. And the prototypical system is, I'm going to draw a picture for the benefit of our new arrival. We were looking at an airfoil with a torsional spring, which rotates through an angle alpha. And the equation of motion for that is I alpha alpha double dot plus K alpha minus Q infinity C E 2 pi alpha equals Q infinity C E 2 pi alpha naught. And this, of course, is the moment of inertia. This is the spring constant. This is the dynamic pressure of the flow. This is the chord. E is the distance from here to some magic aerodynamic center point. 2 pi, it comes from the aerodynamic theory. And the difference between alpha naught and alpha is the twist of the spring, the angle of twist of the spring, while alpha naught plus alpha is the total angle which this makes with the oncoming flow. Okay? And then if we non-dimensionalize that as we are wont to do, we got, of course, dots denote time derivatives. We got alpha double dot plus omega alpha squared 1 minus Q infinity over Q divergence times alpha. This time I remembered to put it in, right? And then what we added in, just for fun and a learning experience, we added in a nonlinear term. Did we just add in alpha cubed? Yeah, just plain old alpha cubed. It's alpha cubed. And then on the right-hand side, we have Q.
It's alpha cubed times...
Oh, I'm sorry, maybe alpha.
We have an alpha dot.
Q infinity over Q divergence omega alpha squared alpha naught. And omega alpha squared, by definition, was the Nash frequency in the absence of any aerodynamic flow. And Q divergence, of course, is when this term goes to zero. If I solve this term for Q, which this term goes to zero, that's Q divergence, and that's K alpha divided by C E 2 pi. And as Kevin would point out to us,
the alpha cube is multiplied by omega alpha squared.
Oh, did I multiply that? Okay, thank you. I've forgotten whether I did that or not. Oh, I have to do it, otherwise it won't be dimensionally correct, right? Thank you.
We had a damping term as well.
Say again?
Damping term. Damping.
Oh, damping. You want to put damping in too?
We did it homework.
Oh, we did homework. Oh. Well, I was going to do the simpler case. Okay. All right.
We would have loved to do the simpler case.
No. The instructor is allowed to do the simpler case, but not the students. And you have to understand how this works. Okay, so we put damping in. All right. Okay, so this is the setup, right? Now the question is how to find alpha. The simplest thing to do is get out your MATLAB manual and look under linear differential equations, or nonlinear differential equations. This is nonlinear, or linear differential equations, and look up the subroutine that gives you the time history of the solution. So that's probably the first thing you would do if you were doing this in real life, right? So you use the software. The software. See, our friends in Stockholm must have given up on us. Software to solve linear or nonlinear ordinary differential equations, right? ODE, ordinary differential equations. And to do that, you'd have to specify alpha at time t equals 0, some value, whatever value you like. One's a nice value, but you could pick something else, and alpha dot. And probably the simplest thing to do is pick that to be 0, although you could reverse these or whatever. So if you do that and write down the differential equation, that's all the software needs to give you the time history. Now, based on the homework you did some time ago without the nonlinear term, you should anticipate the answer, okay? And it will depend on lots of things. First of all, you could non-dimensionalize time, introduce a non-dimensional time, t non-dimensional, right? and write this, and you could divide, what would you do? Divide through by mega alpha squared, and that will make this a non-dimensional time derivative, and then mega alpha would go away. That's what I would do. You don't have to, but that's what I would do. And then the only parameter that remains is Q infinity over Q divergence, right? That's the only thing that can affect the fundamental nature of the solution. So let's think about what's going to happen. We're going to plot alpha as a function of time, or as a function of, thank you, non-dimensional time. Because then the results are universal, right? They don't depend on mega alpha. So what happens if Q over Q divergence is less than 1? Oh, I guess we have to pick, you have to select the zeta sub alpha too, right? So let's pick a nice zeta sub alpha. 0.1, actually that's a fairly large zeta sub alpha. But since I've done this problem before, I know if I pick a larger zeta sub alpha, the transients will be shorter and I won't have to integrate so long time, right? So I'm cheating a little bit. If I pick it to be 0.01, the same sort of thing will happen. It'll just take longer for the solution to reach a steady state. So what happens if Q over Q divergence is less than 1? What do we think will happen? Has anyone actually done this? Okay, what happened? I'm sorry? It oscillates and decays. Okay. And eventually goes to 0, right? Asymptotically. And by the way, you know, I can think of this from here to here. That's a period, right? What's the period equal to, do we think? Based on linear theory. It's not going to change much due to non-linear. It'll change a little bit, but not much. What's it going to be equal to? It's the frequency is going to be omega equals omega alpha times 1 minus Q over QD square rooted, because this is the effective new omega, right, of the oscillation. So it's just the square root of this thing. Okay. That's what happens when Q over QD is less than 1. What happens when Q over QD is greater than 1?
shift.
Yeah. What would happen if Q or QD were greater than 1 and the nonlinear term were not there?
Will diverge.
It would diverge. It just go off to infinity. Well, you know, if you're doing a time march, you're not going to wait till it'd take infinite time to get to infinity, right? But it'll get really big in a relatively short. After a couple of periods of oscillation, it'll get really big, way beyond the validity of linear theory, certainly. Yes.
I saw that depending on whether I was using even or odd numbers. So when I was using Q over QD equal to 2, and then I was also trying to with Q over QD equal to 3, then it was shifted the steady alpha was if it was even, I think it was negative. Then if it was odd, it was positive.
Could be.
And why is that?
Well, we're going to discuss that. Yeah. So let me rephrase what you just said. What you found was when Q over Q divergence was greater than 1, and you included the nonlinear term, right? Including the nonlinear term, that if you wait long enough, there again was some oscillation, but again you reached a steady state. But the steady state was no longer alpha equals 0. It was some finite value, right? And by the way, depending on which Q or QD you picked, right, it was either a finite value plus or a finite value minus. It could be either one, right?
Yeah, depending on whether
an even or yeah. Well, it probably depends on more than that, but we'll talk about it. It depended, right? Okay. So let's look at this equation. Okay. And now that we know, based on time simulation, now that we know that what happens after the transient dies out, for Q over Q divergence greater than 1, we know it reaches a steady state, i.e. a constant value, no longer changing in time. Of course, asymptotically, it's always changing in time, but the changes are so small you can't really see them, right? So let's go back to equation 1 and set the time derivative to 0. Okay? Oh, by the way, when you did the calculation, I forgot about alpha naught. What value of alpha naught did you use? 0 or a small value?
we have a function.
Okay, well we won't worry about what it is. We'll do the case when alpha naught is not 0. So we have to also pick. Should have forgotten about alpha naught. We don't forget about alpha naught. I have to pick that too. Right? Okay, so let's look at equation 1 and set this term to 0. All right, since we know that at large time, nothing is changing with time, right? So we can set that term to 0. And now we can solve, with a little bit of work, for alpha. Okay. So we're going to solve 1 for alpha at large time. And it's really large non-dimensional time, right? Large probably means like, I don't know, 3, 4, something like that, right? Depends on damping, but yeah. Okay. So what do we have? We have mega alpha squared 1 minus Q infinity over Q divergence times alpha plus omega alpha squared times alpha cubed, right? Equals Q infinity over QD alpha squared alpha naught, right? Notice how cleverly I've arranged things. It's got to cancel out, right? The final steady state can't depend on alpha naught because we already saw that we can non-dimensionalize time and get alpha to disappear. Yes.
You still have the damping.
Oh, I'm sorry. Well, no, we're going to throw damping away too, because for the same reason. Well, no, because in the steady state, nothing's changing with time, and therefore damping is just like Q dot. Thank you for asking, though. So I can throw that one. I can throw away the inertia term, and I can throw away the damping term in the long time steady state. Okay, so here we are.
But alpha naught is a constant.
Alpha naught is a constant. I mean, you could do the case for an alpha naught is not a constant. But for this analysis, I'm looking at the steady state. So I'm assuming in your time simulation, you picked alpha naught to be a constant, did you? No, you let it be. Oh, you let it be something else. Okay, well, this is, okay, so special case. Alpha naught is constant. It's not zero, but it doesn't depend on time. Okay? Okay. So, how would I solve this equation? Well, I'll tell you how I would solve it. I would pick Q over Q sub D, and I'd probably start out with Q over Q sub D equals 0, since that's pretty easy, right? Then I would pick alpha and solve for alpha naught. I want to plot, right? I mean, I could, this is a cubic equation. There's actually an analytical solution for a cubic equation if you could use it, but this would be easier if you were doing this by hand. In fact, what I might do is also consider it even super special.
Hey, Jerusalem, are you there?
Hi, Danny.
Oh.
What?
So we just...
Oh, sorry.
You join us.
I wanted to turn the camera towards them, but
Good morning.
Hello.
Hello.
Hello. Oh, we don't know.
Can you see us?
Yeah.
No, but we'll see you in the video afterwards.
Yeah. We are discussing the homework and the effect of the nonlinear term in homework number 4. That's what we're discussing.
The easiest part.
Okay. Ah, there you are. Hello there. Well, so you're in the middle of the movie, so your challenge is to try to understand what happened in the first half of the movie based on the second half of the movie. Okay. But, so let's look at the super special case. The super special case is alpha naught equals 0. All right? And in the super special case, then we have 1 minus Q over Q divergence alpha plus alpha cubed equals 0. Right? And now it's really clear what alpha is going to be. Alpha can be 0. That's one possible solution. Or alpha could be what? If alpha is not 0, I can cancel out 1 alpha, and I'll get alpha squared equals what? Minus 1 minus Q over Q sub D. Yeah, alpha squared. Well, alpha squared has got to be a positive number, although notice that alpha itself can be plus or minus. Okay. But this particular possibility only makes sense if Q over QD is greater than 1, so that this negative times this negative gives me a positive. Otherwise, there's no physical solution. So alpha is 0 for this special case, not surprisingly, for all Q over Q sub D less than 1. And it's not when Q over QD is greater than 1. So if I plot, I call this, I'm going to put SS on here.
Yeah, sure.
SS in steady state. For those of you old enough to remember World War II, don't take this as a political subscript. SS is steady state. So F alpha SS Q over Q divergence. Here's 1. So it's 0 up to here. It still could could be, according to the mathematics, it still could continue to be 0 over here. I mean, alpha equals 0 is always a solution to this equation, right? But then there are two other possible solutions, one of which is the positive number going up like this. The other is a negative number going like this, okay? For those of you, how many of you have ever been on a farm? How many of you know what a pitchfork is? How many people know what a three-prong pitchfork is? This is a pitchfork. And then that's the mathematical term. This is a pitchfork bifurcation. And who's taking Professor Virgin's course in non-aerodynamics? Have you talked about pitchfork bifurcation? Oh, very good. So you will verify that this is a reasonable thing. Okay. Now, when you do the numerical simulation and you wait long enough in time, you will see this solution, alpha steady state equals 0 up to this point. Beyond that point, you'll never see alpha steady state equals 0 in the numerical simulation. You'll either see this solution or this solution. In this case, when I set the alpha naught equals 0, it would depend on the initial condition. If I started out with a positive initial alpha, I would go to one of these branches, and if I started out with a negative value of alpha at t equals 0, I go to the other branch. By the way, it is initially true that if you start with a positive alpha at time t equals 0, you end up with a positive branch. It depends on lots of things, including Q or QD, and actually the damping factor and all that. By the way, if the damping is set equals 0, was you ever set damping equals 0 in your time simulation? You didn't do that. Well, what would happen if you set damping exactly equals 0 in your time simulation? No, you wouldn't. It would be bounded because of the nonlinear time. But you would oscillate forever. You'd never reach a steady static value. There would be no alpha SS with exactly 0 damping because there's nothing to damp out the oscillations. So you just oscillate forever. Now, if alpha naught is not 0, you can work it out. But here's what you find. If alpha naught is not 0, first of all, even if you look back, let's go back to this equation. If alpha naught is not 0, but even though it's a constant, this equation still has to balance at time t equals 0. So you start off with some non-zero value of alpha naught, and then you wait for long enough, and you'll get a solution that looks like this. So this is alpha naught, not 0. Still steady state, still got some damping, still waiting long enough for everything to damp out. But eventually I'll reach a steady state. It goes like this. Or the other possibility, I mean, there has to be some sort of continuity, right? So this pitchfork, now, depending on whether alpha naught is positive or negative, this branch, think of this as going this way, and then this branch goes this way. Or you can, what really happens is there's a branch that starts out here when alpha naught is 0 that becomes this dashed line when alpha naught is not 0, and this other branch goes like that. So the effect of the alpha naught is now to distinguish between, you see, it's perfectly symmetric about plus and minus when alpha naught was not 0, but with alpha naught it destroys the symmetry slightly. And what else can I tell you about this? And you can, by the way, you can find these branches still by solving this, not this equation, solving this equation, right? Which you could do analytically, or you could do using this by hand calculation. Okay. So this is all the case when alpha naught is a constant. So let me pause, because now I think in the homework I actually said you use an alpha naught that wasn't a constant, right? Right. That's harder, but we'll talk about that. Okay, but for the case when alpha naught is a constant, is that helpful? Okay. So when alpha naught is a constant, you really want to know the long time history. You can do a few numerical simulations, see what's going to happen at a large time, and then reduce it to a statics problem. It's nonlinear, but it's a statics problem, which also makes things a bit easier. Okay. What about alpha naught and some function of time? Well, that's harder. You can always do time simulations, right? You can always do time simulations. What else could you do?
You can assume several things. Get something that reminds us of our unlimited solution.
Well, the case that probably is next easiest is still a special case, but it's not quite as special as alpha naught constant. If you let alpha naught be some alpha naught bar cosine omega, I'll call it E time. I put the E on the note, that's a frequency of excitation, right? I'm exciting the system by allowing alpha naught to change with time. Alpha sub omega, omega sub alpha is the natural frequency, the linear natural frequency. But omega sub E is how I'm exciting the system by some external agent. So you can think of it, E is standing for external or excitation or both. I can make it double E, right? External excitation. Yes.
Where you had the term E to the minus lambda E omega T times.
Yeah, on the homework I have. Go ahead.
Would that decay to zero? And assume alpha naught is 0 after a long period of time?
Absolutely.
And then you could do the.
And then you can do the static. Yeah, you're ahead of me. Thank you.
We do the homework again.
That's right. If I let, since you raised that point, if I let alpha naught, give me the formula again.
It's
E
to the minus lambda E omega times T times cosine omega E.
Yeah.
Apparently it's not a lambda because I thought.
I think it's probably zeta, right?
Zeta, so that's the one.
Because it's a decay, but it's a decay associated with the external excitation. So what happens with this alpha naught at large time? It goes to 0. So at a very large time, I can forget about alpha naught, and I'm back to the case where alpha naught is 0. Right? If I really want to know what's happening at large time, So in some ways, this case, if you're only interested in the very large time solution, this case is actually easier than this case, because in this case, the excitation persists forever, right? Now this is actually the special case when zeta E is 0, right? So let's talk briefly about this. I'm not going to go into a lot of detail just yet. I might come back to it later. If I have this case, then let's go back to our equation, alpha double dot plus what? Omega alpha squared, 1 minus Q over TB, alpha plus alpha, omega alpha squared, alpha cubed equal Q sub D, omega alpha squared, omega naught. Okay? And just to make if I normalize the time by omega alpha, right, then I can make omega alpha go away in this equation. Is that okay? So I'll call this now hat, where this hat means a derivative with respect to non-dimensional time. Okay. Now we have an excitation that persists forever, right? If we use this, I'm going to call this equation, I don't know, 3, I guess. So, call that 3 and call this 4. So, again, there are basically two situations. I'm below the divergence value, right? So the system is stable, but it's being excited externally, right? So what form of the solution might I reasonably assume, given that excitation? Oh, I left out the damping. You want to put the damping in? Tough. Okay, I'll put the damping. There's the humidity. Here's the damping. Okay, what form of solution might you assume? Assuming that I'm in the steady state, we already know the transients are tricky, and to really do the transient with the non-term, numerical integration is the only way to go. On the other hand, you don't want to keep doing numerical integrations forever because, for a couple of reasons. First of all, for a more complicated system, they might be very time-consuming. Not for this system, but for a more complicated system. The other is, you don't really get quite as much insight as if you can do something a little simpler and you're primarily interested in the steady state. Right? But in this case, if this persists, if the excitation persists, then the oscillations are going to persist, right? Even with damping. All right. So what form of solution will I assume? Given that this is the nature of the excitation, what might be a reasonable guess as to the form of alpha as a function of time? Cosine? That's good. Cosine's good. What's your prejudice against sine? Well, you might be inclined to just try cosine first, and then you'll see that you really need sine. But let's do this. Let's assume the solution for alpha is alpha bar cosine omega ET, right? I mean, that's excited at that frequency, that respond to that frequency. Actually, we'll see it responds at not only omega E, but 3 times omega E and 5 times omega E and 7 times and so forth. But we hope that the responses at those other frequencies are smaller than the responses at. So if we put that in, so this is going to be 5. If we put 5 in 4, and I'm going to leave the damping term in because you insisted. It'd make it a lot easier if I didn't have it, but then I'm going to have what? I'm going to have minus omega squared, omega bar, cosine, omega ET, that's this term, plus this term will be 1 minus Q over Q sub D, alpha bar, cosine, omega ET. And then I'm going to have plus omega bar cosine omega ET all cubed equals Q over Q sub D. I know I left out the damping term. I'll put it back in. I knew you were going to tell me that. Alpha or not cosines omega ET. And then the damping term is going to be plus 2 zeta alpha omega alpha. If I differentiate the cosine, I get thank you, minus omega E alpha bar sine omega ET. I guess that's it, right? This term goes on this side, right? This term is on the left-hand side. Well, maybe I should do something about the cube term first. Using my trigonometric handbook, I know that alpha bar cosine omega ET cubed is equal to 3/4 alpha. Well, first, I've got an alpha bar cubed, right? Times 3/4 cosine omega e t plus 1/4 cosine omega e, cosine 3 omega e. Right? I mean, that turns out to be even 10. Okay. Now, the way the game is played is I need to balance the harmonics. That is, I need to balance all the coefficients of cosine omega et and sine omega et and cosine 3 omega et. Right? Well, I can't really do anything about cosine 3 omega et. Why not? Well, because I started out with a solution that had this form. If I really thought that was important, I should have alpha bar cosine omega et plus another coefficient cosine 3 omega et. But if I did that, then when I went through this, I'd end up with a cosine 5 omega et. See, I'm always one behind. So in the spirit of let's get on with it, we just ignore the cosine 3 omega et term here. But if we really like 3 omega et, we would put it back here and then ignore the 5 omega et term. You really like that one, you can see what happens, right? But at some point, you got to neglect a higher harmonic in this method. Okay. The other thing we discovered is that our optimism about this was not entirely well placed. Because with damping term, I need a sine term here as well as a cosine term. Otherwise, I cannot balance the cosine term, because the only way I can balance, there's no cosine term over here, right? The only way to generate a sine term is to have it here, and then I'll generate sine terms from this term and also from this term and this term and so forth. Okay. But if I were willing to ignore damping, which I'm going to as a first cut, I mean, I cleared it long enough so you'd see what the difficulty is, right? But it's not an impossible difficulty. It just means I have to go back and put the sine term in here. But that's something that younger, stronger people should do, not those of us who've already done it too many times and don't want to do it again. Right? Okay. So I'm now going to ignore the damping term and balance all the harmonics, just the first harmonic, though, because that's all I can do given what I have seen. Okay, so now canceling out all the cosine omega et that appear in each one of those, I end up with the following. Let's call this equation 6. 7. We have minus omega squared alpha bar plus 1 minus, this is omega e, I'm sorry. Okay. You were too polite to point that out to me. Q reduced to D. I think I'm still calling this Q infinity. Occasionally I'll drop a subscript. I'm sure you will restore it when it needs to be restored. Alpha bar plus alpha bar cubed 3/4. That came from the cube expansion equals Q over QD alpha bar. Okay. Mathematically, this is just the facts problem again, right? Except it has a different physical interpretation. Now this alpha bar is the amplitude of an oscillation. And if there's no damping, this persists forever. Even with damping, this persists forever, right? With damping, you have a modification of this because there's a sine term. sine omega E term, and therefore there's a phase shift between the excitation associated with alpha naught and the response associated with alpha, and you have to take that into account. But it turns out for small damping, this is pretty close for the steady state. So you can obtain the solution this way, and this is almost an analytical solution. And then you can compare that to your time simulation. Isn't that easy? If you've done it before. If you've not done it before, but now you've had this class, it's easy again. Questions? You probably really want to reassure yourself that you understood this, right? And the way to do that would be to include the damping term and the sine term and Berkeley algebra. Don't you think that would be a good exercise? So why don't we assign that as the part of the next homework? Can we do that? So next homework. This is number 5, right? Include damping. Assume alpha is alpha bar C cosine omega E T plus alpha bar sine, if you will, sine omega E T, right? For alpha naught equal alpha naught bar cosine omega E T. Now I'll tell you a little trick. No extra charge. You can put the phase shift in the response. You can put the sine term in the response. You could also put it in the excitation. If you put it in the excitation, then you don't need to put it in response. And since you got a lot more terms, a lot more response than you do excitation, you might want to alternatively, you could let alpha equal alpha bar C cosine omega E T and alpha naught equal alpha naught C cosine omega E T plus alpha naught S sine omega E T. That probably makes the algebra a little more compact and efficient. You should get not the identical answer because the algebra is a little different, but you get an equivalent answer. And you know, if you end up applying something like alpha bar over alpha bar naught, I'll make this absolute value because it's really the square root of alpha bar C plus alpha bar S over alpha bar naught. Or you can apply alpha bar C over the square root of alpha bar naught C plus squared. Should be squared plus alpha naught S squared. I mean, either way, you should get the same answer, right? And hopefully will. But then when you do the time simulations, you can always check that the time simulations are the same answer. And this isn't exact because remember we neglected the third harmonic, so the numerical simulation won't be exactly the same as the other. And it will depend on the magnitude of alpha bar alpha naught, right? Because if alpha naught is small enough, the response will be small enough that you'll be in the linear range, and the alpha cube term won't matter very much. And as alpha naught gets larger and larger, alpha will get larger and larger, and therefore alpha cube will become more significant relative to the alpha terms. Okay, anything, have I told you more than you wanted to know about that? I certainly told you more than you want to know in terms of assigning another homework. I understand that part. But is there anything else that you would like to hear about today? You're okay? Stockholm, did you enjoy the last half of the movie, and are you confused about what happened in the first half?
Yes.
Yes to both questions, or yes to the first and not the second?
Is that working?
You have any questions?
Can you hear us? We're close to the lady. Your questions?
Yeah, we can hear you, but not very well.
Yeah. No questions.
That's good. I heard that. That's a good thing. Okay. Now, I'm going to shift gears and talk about linear system dynamics. Part of the exercise of maybe the really basic take-home message of the alpha cube term is linear system is wonderful and all that, but when you have nonlinear effects, life gets more complicated. And you can always resort to time simulation, but there are other methods that may also be useful. Okay, let's see here. Okay, I'm going to keep that. We'll save that. Okay. I'm going to tell you a few more things about Fourier transforms, and then we'll use that new knowledge and discuss random vibrations in a compact way to look at random response using Fourier transform techniques, which are the way people mostly do it these days. See, this is number 5, is that right? Last page is 4? Yeah. 5. Let me remind you about Fourier transforms. And by the way, we're going to use Fourier transforms when we do our discussion of unstable dynamics. We've introduced the topic of Fourier transforms when we're thinking of functions of time and taking the transforms. We can take transforms with respect to spatial variables too. And that's commonly used to take partial difference equations in time and space, right? And transform them with respect to both spatial and time variables, and reduce PDE to an ODE, which you can readily solve using ODE techniques. And then all you need to do, quote unquote, is an inverted transform. The good news is for classical equations like the wave equation, which is one of the equations we'll be discussing, it's mostly been done. It's in the textbook. Those inversions have been done. And therefore, in some sense, the solution is no, except as you will see, there's still some heavy-duty numerics involved, which is why people like Zona Technology write computer codes and make a fair living marketing those codes to aerospace companies. But anyway, that's just a glimpse of the future. For the moment, let's think of alpha as a function of time. Then we have alpha star, which depends on frequency, which is the Fourier transform of alpha. And that, by definition, is alpha as a function of time multiplied by e minus I omega t dt. And if you give me a function of time, I can, in principle, do this interval, often analytically, but not always. And therefore, this becomes some function of frequency. So, if you will, the transform is just a frequency domain representation of time information. That's what it is, okay? And then the inverse of this, if I'm given alpha star, there's always a 2 pi somewhere. It's alpha star, which depends on frequency, and then I multiply e to the plus I omega t, and integrate overall frequency, and I reproduce the function of time. And for linear systems, the virtue of this is that you can algebraically represent the relationship between the input and the output in the frequency domain, which means the algebra is simpler. And then all you need to do is invert and get the time history if you want that. Now, let's see, I'm going to call this equations 1 and 2. There are a couple of interesting features of this. This is called a transform pair, right? It's a pair of equations. They're actually dual, reciprocal, if you will. I could take this result and put it in here. I could do that, right? or I can take this result and put it here. So let's do the following. Let's take 1 and place it in 2. But to do that, I have to be a little careful. I've got this time, which is related to this time, but this is here in this interval, time is a dummy variable, and I don't want to confuse that time with this time. So I'm going to call that tau before I substitute it in, right? Just so I can distinguish between those two different times. So if you do that, then alpha of t becomes still 1 over 2 pi. The integral it's always integral from minus to plus infinity of alpha star, which is this thing, which is also the integral from minus to plus infinity of alpha of tau. I have to make this a tau also. Tau, e to the minus I omega tau, d tau. And now e to the plus I omega t, d omega, right? Okay. And now what I want to do is I want to interchange, and this is easy to do because the limits do not depend on anything other than they go off to infinity. I want to interchange the integral with respect to tau and omega. Right? I want to do the integral with respect to omega first and tau second. So we'll do that. So let's see, what do I want to do? I'm going to take outside, if I'm going to do tau second, I'm going to take outside everything that doesn't depend on omega, but only depends on tau. And then I have minus 1 to infinity to plus infinity of e to the I omega t minus tau d omega d tau. Okay? And the question is, what is this? Actually, what is this? Including the factor of 2 pi. And I'm going to write this very suggested in the following way. Whatever that is, once I do the integral over omega, it only depends on t minus tau, right? Okay. So I'm going to write it as I alpha naught. Now I'd use that in rotation for something else. I'll use it. It's some function, t minus tau d tau, where this function is by definition 1 over 2 pi, the integral of minus infinity to infinity, e to the I omega t minus tau. E minus tau d omega, right? And all of this must be equal to alpha t. So, forgetting about that definition for just a moment, but just looking at this equation, what do you imagine that f of t minus tau must be for this equation to be true? And this equation says alpha of t is the integral of alpha of tau times some magic function d tau. What must the magic function be? We've seen it before, and you will see it again. It has to be a delta function. That's what a delta function does. A delta function is the thing when you multiply it by alpha of tau and integrate through a time t, produces alpha of t, right? So this turns out to be the delta function. Okay, so what are we so this is a Fourier representation of a delta function. In fact, it's from a computational point of view, an interesting and useful representation. Okay. But there's another way to see the same thing. You know, the delta function is a function of time. Okay. What is the delta? Well, it has certain properties, right? It's infinity, right? It's infinity at t equals 0, 0 everywhere else, but an integral of it is 1, right? So if I'm going to compute the Fourier transform of delta function, I do the usual thing. I put the delta function as a function of time inside the integral and multiply by e to the minus I omega t and integrate with respect to time. If the delta function has this wonderful property, what's the value of this integral? What is the Fourier transform of the delta function?
1.
1. It's equal to 1. Okay. And therefore, the delta function must be, according to the inverse rule, 1 over 2 pi, the integral of delta star, which is 1, e to the plus I omega t d omega. But that's just the same thing. I mean, this is the delta function of t minus tau. This is the delta function of t, right? So another way, you didn't need to do this if you didn't want to. If you wanted to, you could just start with the delta function and its properties, and then compute the Fourier transform, and then find a representation of the delta function in terms of an integral over frequency. So this is the frequency domain representation of the delta function. Okay. I think that's all I want to say about that. Okay, let's now go on. Oops, questions. Or random oscillations. What do I mean by random oscillation? I mean something that never repeats. Okay, never repeats. But we're going to see in a more technical sense what we mean by a random oscillation in just a moment. But for the moment, take it at that. Now, we can look at either alpha or alpha naught. It doesn't matter. Some function of time. I would like to do the following. I would like to take alpha and define, first of all, its mean, put a bar above it, which by definition, 1 over some large time, the integral from minus that large time divided by 2 to plus t over 2 of alpha of t dt. Right? That's the time average. And we're thinking of the limit as t tends to a large number. Okay? So if I have a time signal from a numerical simulation or from experiment, and I know alpha of t, I can compute the mean. Of course, I can compute the mean even if it isn't a random function, right? But in particular, if it is a random function, I might like to know the mean. And so, and for our particular system, given the mean of alpha naught, we like to find the mean of alpha. Okay? And we can do that. And what you will find is that the mean of alpha is the mean of alpha naught times the transfer function from the two. Remember, the transfer function involves frequency, right? But it's not just any old transfer function. It's a transfer function evaluated when the frequency is 0. And the transfer function when the frequency is 0 is just the static relationship between alpha naught and alpha. So if I would just want to relate the mean, and this is true of any linear system, whether it's a random input or not, if I want to relate the mean, it's just a statics problem. And people have known this for a very long time. And we can show that in a couple of lines. But then the question is, okay, if I have a random function, I might like to know something else. I might like to know, let's say I set things up so that the mean is 0. The mean of the input is 0 and the mean of the output is 0. And for a linear system, I can always do that because I can always adjust the level, right? But then what I really want to know is I want to know the fluctuations about the mean. I want to know the mean of the square, the mean square. So that would be defined as alpha squared mean. Again, the same sort of thing. Right? So what is the relationship between, thank you. What is the relationship between alpha squared and alpha naught squared? Knowing this, you might hope that unfortunately, that is not true. Unfortunately, it's not true. In fact, if it were true, life would be so much simpler. But it's not true. So, what is true? Well, it's a longer story, which I'm not going to tell you all about today. But it involves, first of all, generalizing the concept of a mean square and introducing the idea of a correlation function. So let's talk a little bit about correlation function. And this is not a bad name, by the way. It actually, unlike some other names that will appear shortly, it has some fairly clear meaning. I'm going to define the correlation function. I'm going to use the symbol phi, and let's say I'm doing the correlation function for alpha. It's defined to be 1 over t, the integral from minus t over 2, this looks familiar, I hope, of alpha of t. And then if I multiply by another alpha of t, I would get the mean square, right? But rather than multiplying by alpha of t, I'm going to multiply by alpha, a function of t, plus some additional time, which I'll call tau, since that's what the rest of the world calls it, dt. Once I do this integral over t, I still have a tau remaining, right? This thing on the left-hand side depends on tau. If I set tau equal to 0, I get the mean square. But this is the correlation function because it says how some function of time at time t correlates with the same function at a different time. And if it's truly a random function, you would think that as tau gets big, right, as the two instants in time are well separated, if it's random, they don't really have much relationship to each other, or that there's sort of a plus and minus calculation. For a random function, one expects phi to approach 0 as tau approaches infinity, right? Now, you can never go out to infinity, at least not numerically. So if you had a time history and you computed the correlation function, right, you said there are black boxes you can buy that if you feed in the time history, they will produce the correlation function for you. You can look at the correlation function and see if it's decaying as tau gets large. And if it is, then you say, oh, that must be essentially a random function. Okay. Now I'm going to tell you the answer, and then next time we'll talk about it in a little more detail. this is some function of a time variable, tau. So I can take the Fourier transform, right? I can take the Fourier transform, which will be some function of frequency, which by definition is the integral from minus infinity to plus infinity of phi alpha alpha of tau. E minus I omega tau d tau, right? And because I'm now, and you are now, masters of Fourier transform theory, you know that there's another relationship that says, I'm going to put a star here to just give this special designation. There's another relationship that says the correlation function itself is equal to 1 over 2 pi.
Excuse me, Professor.
Yes.
The video feed for the notes is frozen, and we only can see the correlation function written there and nothing else.
I didn't get that. Did you get that?
Yeah.
Guys, I have nothing to do with this right now, so you'll have to get yourself acquainted with the recording. Okay? We'll just finish the 10 minutes.
Yeah, we're almost done. I'm sorry about that.
Sorry, it's technical issue.
The inverse of this is this Fourier transform, depending on frequency, e to the plus I omega t dt. Okay? Okay. Let's see. So I'm going to call this 1, 2, 3. Okay. Oops, sorry. Thank you. That helps. Now, why do we go to the trouble of defining the correlation function this way? Well, one reason is it's a way to test to see if our function really is random or not. Right? That's just one thing. But there's another reason, and that is it turns out the relationship between the input of alpha naught and the output of alpha in terms of the power spectrum, that's what this is called, which is the Fourier transform of the correlation function, is much easier than the relationship between, say, the correlation functions themselves. In particular, after 3 or 4 pages of algebra, which are in the book, you can show that the power spectrum, the power spectrum of alpha is equal to the power spectrum of alpha naught, okay, times the square of the transfer function. But now, of course, the transfer function depends on frequency, and by square I mean h multiplied by its complex conjugate. If I these are both in general complex numbers, by the way, right? But if I multiply a complex number by its complex conjugate, I get a real number, and you'll be happy to hear that. And so the way the game is played is you find the transfer function as before, right? That goes all the way back to sinusoidal inputs, sinusoidal outputs. You find the power spectrum or the Fourier transform of the correlation function of the input. And then you can produce the comparable quantity for the output. And then from here, you can produce the correlation function. And if you really don't want to know the correlation function, but you only want to do the mean square, you set tau equals 0, and you just do the integral of this over the frequency. Okay. Now, isn't that neat? Someone became famous for doing this. S.O. Rock. It was looking at the noise, random noise in electrical circuits, actually, the Bell Labs. So that's why all of this is done. And in aeroelasticity, the random input is usually a random alpha naught, which is due to a gust, some atmospheric gusts exciting an aircraft wing or airfoil, and the response is the motion of the wind. The only difficulty is, well, I shouldn't say only, one of the difficulties, of course, you usually have a dynamical system that's much more complex than that simple plate on the spring, right? You have to think about loads and all the other things you think about for real aircraft wings. But this is the basic idea. I think we've now reached 11:20. I'll come back to this in a little more detail next time. I haven't thought of another homework problem beyond the one I just assigned to you, but I'll keep thinking about it. So I know you will want another challenge. We'll have something to do on random input, so I'll wait and assign that at the next class. Any questions before we break up today?